Everywhere you look, patterns repeat, structures mirror themselves, and complexity emerges from simple rules. It's as if the universe is built on a grand, intricate blueprint that keeps unfolding in fractal harmony. Today, we're diving into the fascinating idea that reality itself might be a vast, self-similar tapestry, a fractal design woven into the very fabric of existence. Stick around if you've ever wondered whether the universe's chaos is just a hidden order, waiting to be uncovered through the lens of fractal geometry. What if understanding these patterns could unlock secrets about our universe, consciousness, and the nature of what's real? Let's explore the fractal design of reality, something both mind-expanding and deeply rooted in the way everything connects. The concept of fractal geometry in nature and science. Fractal geometry challenges traditional notions of shape and structure by revealing patterns that repeat across different scales. In nature, this kind of self-similarity can be observed everywhere, from the branching of trees to the rugged contours of mountain ranges. For instance, the veins in a leaf mirror the larger network of branches, and the jagged outline of a coastline maintains complexity regardless of the zoom level. Such patterns demonstrate that complexity emerges from simple, recursive processes, and they often serve functional purposes, maximizing surface area, optimizing flow, or providing resilience against damage. In scientific applications, fractal concepts extend well beyond visual resemblance. They are instrumental in modeling phenomena that exhibit irregular, complex behavior, such as the distribution of galaxies in the universe or the patterns seen in turbulent fluid flows. Unlike traditional Euclidean geometry, which describes shapes like circles and rectangles, fractal geometry embraces irregularity and infinite detail. This has paved the way for advances in fields like computer graphics, where generating realistic landscapes and natural textures often relies on fractal algorithms. The Mandelbrot set, a mathematical representation of complex fractal patterns, exemplifies how simple iterative equations can produce infinitely intricate images that echo natural forms. Biology offers some of the clearest examples of fractal structures in living organisms. Lungs, for example, are composed of a branching network of bronchi and alveoli, maximizing surface area for efficient gas exchange, an arrangement that perfectly illustrates fractal principles. Blood vessels also form a fractal network, ensuring blood reaches all parts of an organism with minimal effort. Such hierarchical systems are not random, but have evolved to optimize functionality. Recognizing the fractal nature of biological systems has led to innovative approaches in medicine, such as improved imaging techniques and the design of artificial organs that mimic these natural fractal patterns. The concept of fractals extends even into cosmology. The large-scale distribution of matter in the universe appears to follow fractal patterns up to a certain scale, with galaxies clustering in complex, self-similar arrangements. Although this pattern becomes less apparent at enormous scales, it highlights the principle that natural structures, regardless of scale, often display recurring motifs. This recurrence suggests that understanding fractal geometry is key not just to describing individual phenomena, but to grasping the interconnected, recursive fabric of reality itself. It's a lens that reveals underlying order within apparent chaos, hinting at a universe built on simple, repeating rules that generate breathtaking complexity. Mathematical foundations of fractal structures. Fractal structures are inherently rooted in the realm of mathematics, leveraging principles that describe complex, self-similar patterns across different scales. At their core, these structures emerge from recursive processes, repeating a simple operation infinitely or until a desired level of detail is achieved. The foundation lies in the concept of iterative functions, which generate fractal geometries by repeatedly applying a transformation to points or shapes. Take the Mandelbrot set as an example. It's formed through iterations of simple quadratic functions, with each point tested for boundedness, the result being a boundary that exhibits infinitely intricate detail, yet arises from straightforward calculations. The mathematics behind fractals often hinges on complex numbers, particularly when dealing with the dynamics of complex quadratic polynomials. The use of these numbers facilitates the creation of phenomena like bifurcation diagrams, where tiny changes in parameters lead to dramatically different patterns. Fractal geometry also relies heavily on concepts like scaling and self-similarity, properties that are formalized through Hausdorff dimension, a measure that extends traditional notions of dimension to account for fractal complexity. Unlike classical geometric shapes, fractals frequently possess non-integer dimensions, underscoring their intricate, layered structures that defy conventional spatial intuition. Powerful tools from chaos theory underpin the study of fractals, linking initial conditions to unpredictable yet patterned outcomes. The logistic map exemplifies this connection, with simple polynomial equations producing seemingly random but statistically structured populations. These mathematical models emphasize that even deterministic systems can produce complexity at every scale, a hallmark of fractal patterns. Moreover, fractals are intimately connected to the field of measure theory. They often require specialized approaches to quantify their size or complexity within a mathematical framework, expanding traditional notions of area, volume, or length into the realm of fractal measures. Practically speaking, the mathematical foundation of fractals extends beyond pure theory. It's embedded in computer-generated graphics, signal processing, and natural phenomena modeling. Algorithms designed to generate fractals rely heavily on recursive formulas, which can be optimized for efficiency through techniques like escape time algorithms or iterative depth control. Examples include the generation of realistic landscapes in computer graphics, where terrain features exhibit natural fractal self-similarity, or the analysis of ecological systems that display fractal branching patterns. The deep mathematical principles governing these patterns allow us to decode, replicate, and even harness the complexity of the natural world within technological and scientific frameworks. Manifestations of fractality in the universe and reality. In nature and the universe, fractality manifests as repeating patterns that appear at multiple scales, creating an intricate harmony that reflects an underlying order. Consider the branching of trees and rivers. Each fractal branch or tributary mimics the whole structure, regardless of how small or large the system is. This self-similarity extends far beyond flora. The coastline of a continent, for instance, exhibits rugged detail whether viewed from space or up close. Its jagged edges, with jaggedness repeating at various magnifications, is a vivid example of fractal geometry in the natural world. Cosmological structures also reveal fractal-like characteristics. Galaxies don't arrange themselves randomly, but form clusters, filaments, and voids that repeat and mirror larger structures across immense scales. On a cosmic level, galaxy distribution resembles a web-like pattern, with dense clusters connected by filamentary structures spreading across billions of light years, each segment reflective of the larger network. This web-like fractality suggests an underlying pattern in the fabric of space-time, hinting that the universe's large-scale architecture holds self-similar properties just as smaller systems do. Zooming into the microscopic realm reveals fractality within biological systems. The branching pattern of bronchial tubes and lungs, the vascular systems within animals, and even neuron networks in the brain show fractal organization. These biological fractals are highly efficient, allowing for optimal transport of fluids, nutrients, and electrical signals. Their self-similar designs, repeating at different levels, demonstrate how fractality isn't just aesthetic, but is rooted in practical, evolutionary advantages that shape complex life forms and biological processes. Even in the realm of human-made structures and technological systems, fractal principles emerge. Urban cityscapes often resemble fractal patterns, with neighborhoods, streets, and blocks repeating similar layouts regardless of scale. Digital data, such as internet networks or file systems, can be modeled through fractal algorithms that optimize redundancy and efficiency. These examples underline how fractality pervades not just natural phenomena, but also the structure of human experiences, hinting that the fractal nature of reality might be woven into the very fabric of existence itself. Implications of fractal design for understanding existence. The concept of fractal design reveals that natural and cosmic structures often exhibit self-similarity across multiple scales, implying that the universe's fabric isn't smooth or uniform, but rather composed of repeating patterns that recur infinitely. This realization suggests that understanding the nature of reality requires recognizing these patterns at various levels, from the microscopic intricacies of biological systems to the vast expanses of galaxy clusters. For example, branching structures like blood vessels or river networks display similar fractal geometries, highlighting how efficiency and connectivity are woven into the very blueprint of life and matter. Recognizing this fractal nature enables scientists and philosophers to approach existence not as a random assemblage of isolated phenomena, but as an interconnected, nested hierarchy of ordered complexity. One significant implication of a fractal perspective is the idea that chaos and order aren't mutually exclusive, but are intertwined within the universe's structure. Fractals are often generated through simple iterative rules, yet they produce infinitely complex forms, patterns that are both predictable and unpredictable at once. This duality mirrors the behavior observed in quantum physics, where particles follow probabilistic paths that seem random but are governed by underlying laws. The fractal design thus encourages a view of reality as a landscape of nested patterns, each layer reflecting broader principles that govern the whole. Such an outlook can foster a sense of unity and continuity, suggesting that individual experiences and seemingly chaotic phenomena are part of larger, comprehensible patterns that resonate across scales. Exploring the implications for understanding consciousness and the universe, the fractal model points toward a universe capable of embodying self-similarity in its mind-body interactions, planetary systems, and galactic structures. It hints at a cosmos where microcosms mirror macrocosms, possibly offering insights into how consciousness itself may manifest through fractal mechanisms. The idea that neural networks, not unlike fractal patterns, generate cognition implies that consciousness might be a fractal phenomenon rooted in the recursive dynamics of the brain. Moreover, the idea extends beyond the physical. Societal, cultural, and spiritual systems might also display fractal characteristics, reflecting a universe where the pattern repeats in different domains of existence. Grasping this can inspire new ways to approach issues such as complexity management, systemic resilience, or even the search for meaning in life's interconnected web. In exploring the fractal nature of reality, one encounters the profound concept that the universe exhibits self-similarity across all scales. This means that patterns we observe in small phenomena often echo larger structures, revealing a repeating, nested complexity. For example, in natural formations such as coastlines, mountain ranges, or cloud formations, the irregular contours display similar roughness regardless of whether we zoom in or out. This inherent repetition across different magnitudes hints at an underlying blueprint, a fractal architecture that shapes existence at every level. Within this context, the fifth core aspect emphasizes how this recursive structure influences the fabric of spacetime itself. At the microscopic scale, quantum fluctuations can be viewed as miniature fractal patterns, with energy fields fluctuating in a seemingly chaotic yet patterned manner. As these quantum events aggregate, they contribute to larger formations, particles, atoms, molecules, that mirror the same fractal complexity. On a cosmic scale, galaxies and star systems form within cosmic webs that exhibit fractal properties, with clusters nested within larger clusters. This suggests that the universe isn't a random disarray but a nested hierarchy of patterns repeated infinitely, reinforcing the idea that fractality isn't just a mathematical curiosity but an intrinsic feature of reality. This recursive nature extends into the realm of consciousness and cognition as well. Human perception often mirrors fractal structures. Our neural networks are densely interconnected with patterns that resemble fractals, allowing for efficient processing of complex information. The brain's dendritic trees branch out in fractal-like ways, optimizing connectivity and functionality. Similarly, many artistic and conceptual traditions, from fractal art to certain philosophical doctrines, draw upon this self-similar patterning to explore the nature of consciousness and perception. These instances suggest that fractality doesn't just exist outside us in the universe, but also within the very mechanisms by which we experience and interpret reality. Examples from various disciplines underscore the pervasive influence of fractal structures. In biology, The branching of blood vessels and bronchial trees reflects fractal organization, maximizing surface area while minimizing energy use. In ecology, patterns of vegetation distribution and river networks display fractal geometry, demonstrating how nature optimizes resources and connectivity through repetitive patterns. As a fundamental aspect of the universe's design, fractals serve as the scaffolding of reality, guiding the formation and evolution of complex systems from the quantum level through the cosmic scale, tying everything together in a beautifully nested, infinitely intricate pattern. As we wrap up, it's fascinating to reflect on how the intricate, fractal-like patterns echo throughout every aspect of existence, from the tiniest particles to vast cosmic structures. The idea that our reality is built upon recursive, self-similar designs invites us to see the universe not as a random chaos, but as a beautifully interconnected tapestry. You might find it empowering to notice these patterns in daily life, recognizing how interconnected everything truly is. Thanks for joining me on this journey into the fractal nature of existence. If this sparked your curiosity, be sure to stay tuned. There's so much more to uncover about the hidden structures shaping our reality, including deeper dives into consciousness, quantum physics, and beyond. Hit subscribe or follow if you want to continue exploring these fascinating patterns together. Until then, keep observing the extraordinary in the ordinary and stay curious.